Welcome to my presentation, my term paper presentation on electrochemical challenges in lithium sulfur batteries. So, just a small introduction to lithium sulfur batteries. Lithium sulfur is a very promising area of batteries because of their high theoretical specific capacity, which is 1675 milliamp hours per gram, and their very high energy density, which is about 2500 watt hours per kilogram. And the advantage is that having a sulfur cathode, it's one of the most abundant elements in the earth's crust. Its sulfur is low cost, and sulfur being a waste for many industries is considered to be very environmentally friendly. But having a setup of a lithium sulfur battery has multiple challenges, and I'm going to talk about the cathode side of the challenges. Like, there are challenges with the anodes, but that is more specific to the lithium anode, which is more of like dendrite formation and stuff like that, which has been discussed in class, and I won't go into that. I will discuss about where there are problems due to the sulfur cathode in general, and where that affects the electrolytes and that affects the anode. That is what I will be discussing. So the main challenges include, firstly, the polysulfide shuttle effect. I'll get to what that is. Then second, which is something that happens with a lot of materials, which is a problem with volume expansion contraction of the cathodes. Third is the fact that sulfur itself has poor conductivity. Third is that lithium and sulfur together, even though they have good electrochemical benchmarks, they have slow or sluggish redox kinetics. So getting to the first one, which is the polysulfide shuttle effect. Essentially what happens is that the sulfur cathode essentially gives out sulfides. Cathode being the reducing electrode reduces the sulfides and the sulfur to form higher polysulfides, which are very soluble in the electrolytes of the batteries, and those migrate to the anode side of the battery. So this is shown here in the case that these S2N minus goes to the anode side, and of course the anode being oxidizing electrode then oxidizes these higher polysulfides to lower polysulfides, and then they go back to the cathode. So that is, they sort of shuttle back and forth, and that leads to more problems. But essentially there are problems that take place in each of the three segments, which is the anode segment, the electrolyte segment, and the cathode segment. So the problem with the cathode segment is that, of course, the fact that the sulfur itself is getting reduced to these higher polysulfides and then getting dissolved into electrolyte. It means that the active material of the battery or the active material of the electrode is now getting dissolved and is getting lost. Essentially there is loss of active material, and that leads to void formations in the cathode, and it leads to a reduced capacity because, well, the active material is getting lost. Secondly, when you come to the anode side, as a result of this cathode effect, these lower sulfides, which is then like lithium sulfide, when they are not going over to the cathode side, they get precipitated onto the lithium anode, and these have lower conductivity, which is something I will get to later on how that specifically affects the cathode. But yeah, they have lower conductivity, and they are also insoluble. So they essentially form this low conductivity and insoluble layer on top of the anode, which reduces the reactive area of the anode and the reactivity of the anode, and essentially a lot of loss of performance of the anode. And thirdly, we have the electrolyte, right? There is, because of these higher order sulfides getting dissolved into the electrolyte, there is an increase in viscosity of the electrolyte, which in turn reduces the conductivity of the electrolyte, and that is also very detrimental to the battery capacity. And you can really visualize the effect from the picture I have added here from this website. So moving on to the second effect, which is the volume expansion contraction effect. So then again, like I had mentioned before, this is something that is not very specific to sulfur, which happens to different elements. It happens with silicon. It also happens with some metals, like I have seen it happen to on a lower scale to I think palladium. But yeah, so the crux of this is that elemental sulfur and lithium sulfide have a huge difference in density, and that means that the volume they require is very different, which means as and when the redox reactions happen, there is an expansion and a contraction that happens at the cathode side, and there is a huge mechanical stress that is going to be applicable to the cathode side, and this is going to lead to like failure and just mechanical stresses, which lead to probably lattice deformations, which could affect intercalation, or it could lead to cracks. Now I'll talk about 2 points, which is how like cracks is going to worsen like the shuttle effect. Basically what cracks do is cracks allow electrolytes to reach deeper into the sulfur anode, and that means that more parts of the sulfur anode are now getting reduced and now falling to the shuttle effect, and there is now more loss of active material and more fresh surface is getting exposed to shuttle effect, and that means that the capacity is further lower. So shuttle effect is worsened due to this volume expansion, which makes it a lot more detrimental as compared to just the mechanical aspect, as it's like a chemical aspect added on top of it. But also there is huge mechanical stress, and just the structural integrity is compromised, and you would have to work around it through probably structural engineering to have reinforcements to make the electrode stronger. So the third point is that essentially electrode sulfur, elemental sulfur, and as I mentioned before, lithium sulfide, they are low conductivity compounds and elements. Like their conductivity is very low. In fact, I have written down it's as low as elemental sulfur being 5 into 10 raised to minus 30 Siemens per centimeter, and lithium sulfide being 9.21 into 10 raised to minus 9 Siemens per centimeter, right? So these are the compounds that are forming the bulk of the cathode, which means even if the electrochemistry of all the other compounds is fine, there is a limiting factor in the electron transfer inside the cathode, and that is the fact that the cathode materials are lower conductivity materials. So to work around that, you could have basically the electrochemical brute force way would be just higher polarization, and you work around the fact that they have lower conductivity. But the materials way is that you probably put additives, conductive additives, and an example of that would be as I've discussed in my term paper, and as I found in literature, is that probably add like a conductive carbon matrix, which would then not only act as a conductive framework, but also probably, as I discussed before, would act as a supportive mechanical framework. So what it does is it facilitates conduction of electrons through the cathode, which is going to help with this low conductivity problem of the electrode. I think the final problem, which is also very detrimental overall, is the problem of just generally the kinetics issues that are faced with lithium sulfide. Like that is image here for you to just to help you visualize what the kinetics are, and just the charging and discharge curve, and with kind of a metric of how the kinetics of the reaction actually are. Some parts of it are really fast, but as you see, as you go into like the sulfide area, and you go into the lithium sulfide area, where the lithium sulfide and lithium sulfide formation and decomposition, both on the charge and discharge curve, it's blue, which means, like on the scale, it's really slow. And yeah, if you look at the reactions, they are really complex. They are multi-stage, multi-step, and there are multiple electron transfers, and they're characterized by slow kinetics. But there are 2 points that we need to focus on in like the kinetics issues. The first being that the intermediates in the reactions are polysulfide, long chain polysulfide intermediates, and then this like goes back to like the old enemy of the lithium sulfide battery, which is the polysulfide shuttling effect, which means that when the reaction intermediates are these long chain polysulfides, these again get dissolved and dissolved into the electrolyte, at least at the surface, and lead to a loss in sulfur and cause issues, and just lead to an exaggeration and a huge loss of active material. And the second problem is the incomplete utilization of active material, which stems from a more thermodynamic kinetic aspect, which is that the transition to lithium sulfide, which is Li2S, is a solid liquid solid transition, and there is a formation of Li2S2 compound, which precipitates out of the liquid phase sometimes. And because sulfur is our active material, and we have a not wanted product which contains sulfur that precipitates out in this reaction, it leads to the loss of our electrode's main active material, and that is not intended, that's not what we want, and that is also a problem. And that also needs to be dealt with before we can go on and commercialize the lithium sulfur batteries. So in conclusion,